So this slide here just shows the very basic kind of inconvenient truth for a lot of us, how we treat water. I think Water 4.0 does a great job kind of walking through the evolution of how we got here. I think we started with wanting to treat the water coming out of the river, and then we realized also we should probably treat the water from our sewage before we put it in the river. The point is here, uh, uh, one of the major topics here is water recycling. And there's a great video about that in the module and the use of purple pipes, and we're going to go into that here during this talk. But one point to make here is that by default, by our very system of taking sewage water and treating it and discharging it to the river system, and then having that as an intake to another plant, well, that is de facto water recycling. We're using this water over and over down its course. And I understand that if you live in Mississippi at the bottom of the Mississippi River watershed, some of that water that you're taking in there has gone through this process quite a few times, 4, 5, 6, or 7 times through this loop here. Another thing to point out here, and it's kind of a hot ongoing debate about water recycling, it seems like a really good idea to take water coming into the wastewater treatment plant, and instead of just putting it into the river, taking that water and having it go back out into the community for agriculture or any of that kind of use. And that is a good use of water, but at the same time, if you're in a very arid area, you have to acknowledge that when you take some of this wastewater effluent and instead of putting it in the river system, you take it and put it back in the community, you're taking it from the river. And certainly in Southern California, this is coming up a lot. There are projects proposed to recycle wastewater for good uses, but there are people downstream that say, hey, we want that water. That's part of our water right, which we'll get into in another module or two down the road. And they call that, when a river is dominated by effluent, there's a fancy term for it, effluent-dominated river. So there are rivers in Southern California where the majority of the water in that river, making the habitat, supplying downstream users, is sewage effluent. That's just the way it is. So there is and again, I think Water 1.0, Water 4.0, the book, does a pretty good job just walking you through the process of pre-treating surface water before drinking. I think, again, a lot of us, because our society has made these treatment plants sort of top secret or kept them under wraps, people aren't usually familiar with all that happens to their water. But if you take water out of a lake or river, it goes through a lot of pre-treatment, mostly because natural water has lots of little suspended particles, turbidity, and those little particles, we don't want those in the drinking water. And so there's quite a bit of actual chemical treatment of the water before it gets to the tap. You add chemicals to coagulate the little particles and settle them out and then filter it. And then finally you boost the water with chlorine before sending it out into the system. This little video here, it's also in the module. It happens to be the Sydney Water Authority or whatever. It's a great 3-minute video that talks about this process very clearly. And so the key terms there are the coagulation and flocculation and filtration are the main steps. Turbidity is the water quality parameter that is sort of the enemy. And then finally, I want to emphasize one other thing here, is if even after all this coagulation and flocculation, you can get bits of carbon, dissolved phase carbon, and when that dissolved phase carbon gets chlorinated, it creates a class of compounds called trihalomethanes, and trihalomethanes are carcinogenic. And so water treatment plants are constantly dealing with this problem of chlorinating enough for the water to be disinfected, but not chlorinating it so much that they produce too many trihalomethanes produced from chlorinating natural organic carbon in the water. So in the module, there's a little news story about that. It kind of illustrates how local news likes to make people scared and make problems worse than they are. But it's a real big problem. Um, Water companies are always worried about having too much organic carbon coming into their inlets because they know at the end they're going to have to be worrying about trihalomethanes. Okay, on to treating sewage. Great topic. And the idea of a sewer shed. This is a map of the service area for the Sacramento Regional Sanitation Sewer Plant. It's that little ball way down here in Elk Grove area that takes sewage from all the surface area, brings it to this one plant, treats it, and discharges it to the Sacramento River. Kind of strange. Sacramento River is actually a tidal river. It changes direction in response to the tides. So they have to be able to store their treated water and wait for the tide to be going out before they release it so it goes downstream. They don't want to take their treated sewage and have it go upstream. Not what they want to have happen, even though it's highly treated water. Anyway, just to say, we've gone over the concept of a watershed, probably way more than you want. Now we're going to talk about the sewer shed. And there's a 3 or 4 page article about that, new ways to think about the sewer shed and what we're putting in it. Because, we don't care to think about that. We think about toilets and all that. That's one thing, that's gross enough. But we also have industrial waste and some mix of chemicals going into the sewer plant that this poor little dot here has got to treat and put out back into the environment to be safe. So our approach is just make all the chemicals you want, dump them down your sewer, and then hope that the plant can treat them all. And that might not be a great model going forward. There's another thing about, particular to Sacramento and a few other cities. We have in Sacramento an old system. And in the olden days, it was just like the Romans in Water 1.0. Wastewater, or water coming off the street, was combined with water coming out of the toilet in a combined sewer system. And that is old school. Nowadays, obviously, we have stormwater pipes that drain streets and keep that as stormwater, so it's relatively clean and can go right back to the river. We take sewage in sewage pipes and pipe those separately to go to the sewer plant. But there are places where it's combined, and lo and behold, Sacramento is one of them. And the way that system works, if you have a combined system, it's not the end of the world. So here we have sewage from a house, and we have stormwater from a street drain going into the same pipe. Okay. All that water goes to the wastewater treatment plant. So no worries, all the stormwater gets treated. The problem with this is, though, when it rains really hard, the sewer plant can't handle all that water. And so these systems, there's one in Santa Monica that's famous, these systems have to have a bypass for the heavy rains. And so during a heavy rain, sure enough, the combined stormwater and sewage can't, the sewer plant hits its maximum and all that goes to the sewer plant, but that extra goes out into the river. And so like in Santa Monica, there'll be notices of a heavy storm, stay off the beach, because there's been raw sewage that's being dumped into the ocean. Here it is, 2020, and we're still dumping raw sewage out into the ocean. And that's partly because to fix this is very, very expensive. Anyway, there are other problems with having this combined system in Sacramento, and that when these things fill up, and there's a cool little City of Sacramento illustration of the McKinley water vault. I don't know if you've been to McKinley Park lately with all that construction, but it explains what's going on there to address that. Pretty interesting. Okay, so this is sort of more the classic environmental water science view of what you should know about how sewage is treated. And so I might ask you on a midterm or something just to describe the basic steps. And what's primary treatment, what's secondary treatment, what's tertiary treatment. I think Water 4.0 does a good job with this activated sludge business, why that's there. And we know from respiration why aeration is so important. We need to add that oxygen as the electron acceptor so that the bacteria can take the organic molecules we put in this system and respire those compounds into ultimately carbon dioxide and water. Now, here's a trick question. What if you had a lot of sodium chloride or TDS in this wastewater? Is TDS removed from any of these processes? Does it get removed by the screen? Does it fall down as grit? Does it get biodegraded or respired by bacteria? Does it get destroyed by liquid chlorine disinfection? The answer is no. Nitrate, sodium chloride, calcium sulfate, TDS, salinity shoots right through here. And so we need to be concerned with compounds that just don't get treated here. Viruses and bacteria, which was our main concern, do get treated, which is a great thing. But we have to also be concerned with chemicals that might make it all the way through the system. So this is a very busy slide, and I just want to introduce you to this, how this works right now in California with the law of the land. Here is called Title 22. It's a regulation in California that regulates how treated sewage can be reused and recycled. And there's a concept here called fit for purpose. And so here we start with municipal wastewater. And the first stage, undisinfected secondary treatment. So that means the water has gone through here. It's gone through grit and sand removal. It's been aerated and clarified, but it has not been disinfected yet. You can use that water, but you can imagine the uses are pretty restricted. You can, non-food trees, non-milk pasture, things like that. And the concept here is as you get more and more treated down the road, you can get better and more uses that would involve potentially more human contact. That's the whole concept here. And then finally, the big deal is more and more after tertiary treatment, we're adding more treatment steps onto this water to actually use it for human consumption again. And that's a pretty big deal. So right now, it's allowable with full advanced treatment, reverse osmosis and oxidation after tertiary treatment. You can use that water to replenish the water supply. And there's a really good, the end of the KQED video talks about that and shows it really well. And I'm going to kind of hammer that home quite a bit. But anyway, so we do have legislation in California that dictates how sewer plants need to treat the water and what can be done with the water as through the treatment train. So here's another slide that illustrates the treatment train. And again, I just want you to be aware of the basic technologies that are used to treat sewage. This over here to the left, the low is the traditional, biological nutrient removal. Then here on the right is when you can take the water that we normally would put to the river and we treat it further. All these treatment trains are in use right now. You can put it through carbon to remove more organic matter, disinfect it with ultraviolet light or chlorine, put it in a wetland, and then have that ultimately go back to a drinking water treatment plant, DWTP. So this is the idea of taking sewage water, treating it many stages, and having it go back to the treatment plant and all the steps in between. The most popular one that we have in California here is this one. This one with ultra microfiltration, chlorine reverse osmosis, and then after it goes through that reverse osmosis, hitting it with UV, ultraviolet light, and other advanced oxidation. And then after the water goes through reverse osmosis and UV zapping it, it's very hungry water. If you put that in a pipe, it would corrode the pipe because water loves to have calcium and chloride and other natural minerals. And so after they treat it to this standard, they literally have to add earth material back into the water. Otherwise, it'll corrode the heck out of everything. And then you can see they maybe send it through a natural system or may just send it right to a drinking water treatment plant. There's kind of a funny thing in the KQED video, I think it's kind of funny, that says a lot of times water plants will put the water into a wetland or groundwater because it makes people feel better that the water is kind of coming from nature after all, rather than confronting the fact that they're really just drinking their own sewage. Okay. Um, Now, the other concept I want to introduce here is the concept of the chemical of emerging concern. Because, like I say, what chemicals might there be that make it through this process that we should be concerned about, but we're not even monitoring for? And so it's caused the water treatment community to really look at this idea of a chemical of emerging concern and confront the fact that we have tens of thousands of chemicals out there, and we don't even know how to. They're proprietary. I mean, the labs don't know how to analyze. They don't even know what to look for, let alone how to analyze them, let alone what concentration is okay. So these are just a partial list of all the different types of chemicals that are in our environment. And this is a little cartoon that just sort of says, hey, these are how these chemicals can get into our environment. Directly from a farm, different pesticides and herbicides, personal care, PCPs, personal care products, just a whole wide variety of hormones and vitamins. We're finding Tylenol in the water, Tylenol making it through the wastewater treatment plant. Oh boy, what's coming out of the hospital and into the sewer? I mean, like I said before, the hospitals are more and more taking human bodies that are no longer with us, and instead of burying or burning, they just dissolve them in various solvents and put them down the sewer. That goes to the wastewater treatment plant too. So what chemicals are making it through the system into the river? And then, of course, we take the water out of the river just like it was brand new, treat it a little bit, and drink it. So this is a big topic now. It's causing a lot of studies and surveying waterways for these exotic chemicals that might be in the environment. And again, a real tight focus on, are these chemicals being treated adequately, and how do we know? So here is, we've had a long history with this. And this is a nice chart that Kleinfelter consultants put together. It's not complete, and it's not like an academic reference, but it just sort of gives you an idea how, you go through a process here. A chemical company makes the chemical, sells the product, out it goes. You discover it, you put it in commercial use. Later you may find out there's a problem about it. Then we detect it in the environment, then we develop regs on the back end. And that's kind of, a lot of people are talking that, we shouldn't, this model of just making any chemical you want and then later finding out if it's a problem, and then later finding out it spread all the heck over the place, and then later developing regs 100 years later, might not be the best way to manage chemicals into the future. These are some of the ones that have gone through this process. Lead, you've probably, I don't know, I'm old enough to know when I used to put leaded gas in my parents' car. And discovering it all lead all over the environment, and then eventually coming up with bans on leaded gas and alternatives. And these are other examples. The hottest one now is this PFAS. This is short for perfluorinated compounds. They are a class of compounds that are potentially known as forever chemicals because they really don't break down in the environment. They persist. And so we're detecting PFAS chemicals, classically like Scotchgard, fire retardant. There's a lot of uses for these, and the problem is, again, we're in this section of the PFAS, wondering about the health concerns and finding it everywhere before we can develop regulations and alternatives around it. We're in the middle of the PFAS. So this is just an illustration, not to scare you, but there's, something like 80,000 of these chemicals out there, and the ones we know about is a subset versus the ones we don't know about. I will say for pesticides and herbicides, I think, the federal government got on top of that quite a bit in the think I can't remember, the 70s or 80s, because of Silent Spring and DDT. So if because pesticides and herbicides are applied widely in the environment, it's recognized that they need to have a rigorous permitting process. So if you want to register a pesticide or herbicide with the federal government and California, you need to demonstrate that that herbicide or pesticide biodegrades rapidly, that the breakdown products aren't toxic, it's safe to use in the environment. So pesticides and herbicides are being watched. There's still an issue in some cases, but it's nothing like sort of the industrial chemicals where you don't really need to do that demonstration to put a chemical out on the market. Okay, so I wanted to end this lecture. I'm not going to walk through each slide. I just wanted to point out a couple of things about this. Is a presentation that the engineer from the Orange County Water District made. Orange County's down there in Los Angeles, and it turns out they are world pioneers in water treatment. They have the world's largest advanced water purification project to get water from the sewer back to potable use. I mean, that is the world. That includes, obviously, Israel and Australia, other countries, arid countries that are really innovating at a rapid pace. Turns out, say what you want about LA, but they're leading the way. So this is just a really neat story about how a water agency got a lot of folks together and started to manage an entire watershed and attack their problems. So this is a huge area that the Orange County Water District covers, and this what they do is take sewer water and then they treat it and they put it back into the groundwater. So much so that 30% of the recharge water for groundwater is recycled or reused water. That's fantastic. They're trying to get this imported water from the Delta down because they see the writing on the wall that we're going to be fighting to have less and less water pumped out of the Delta to get it restored back to healthier and healthier ecosystem. Natural recharge, 17%. It doesn't rain much there in Orange County. And so this is just not a very typical pie chart. Usually, folks rely down south on mostly imported water with a little bit of recharge naturally. These folks have really stepped it up on recycled and reuse. And this also is it's kind of a funky cartoon, but from the map view, you see the Pacific Ocean here at C, and then the headwaters of the Santa Ana River at A, and then these recharge basins. So what they do, they collect sewer water from this whole area, they treat the heck out of it, and they pipe it back up, treated after reverse osmosis. You can drink it, you can do anything you want with it. They put it in these recharge basins and have that recharge the entire groundwater basin. So now all these cities and towns, their wells are fine, they pump out the water, everybody's happy. In the cross-section view, it looks like this. They treat it down here, they inject it up here, and it's kind of this big cycle. The other thing that happens, and I think I covered this in the groundwater, is because they were pumping the groundwater so hard in here, it was bringing in the seawater and ruining the aquifer with salt water. They take some of the water that they treat and put it in these injection wells, and that shoves the seawater back. So again, they started to do this innovation 30, 40 years ago, and they've been really leading the way. Actually, I'm sorry, since the 70s, 50 years ago. So there's just some neat facts in here. I'm not too interested in those. You could look at them if you wanted to look into this further. The other thing I wanted to show you was a cool slide. Well, this one here. So this is a kind of a conventional pretreatment for water with a flocculation and sedimentation and chlorination and filtration. They have really led the way in what's called microfiltration, which is just super well engineered fibrous material that you can just draw the water in, and it's not reverse osmosis, but boy, it really filters out a lot of stuff. And they do this on a huge scale, and it really is an efficient way to get the good water out of the sewage and move it on from there. And then reverse osmosis. They have the world's largest reverse osmosis plant. And so that then, after reverse osmosis, the water is basically just H2O molecules. And then after that, they zap it with UV light. And then after that, again, because people are scared of sewage, they put it in the groundwater. And then everybody pretends that it's fresh groundwater, and the system works pretty well. Yeah, I think that's all I wanted to say about this. Anyway, check out the other um, articles and mini videos in the unit, and hope that's helpful.